So those of you that are watching at home, welcome. We're going to work an example using the rational root theorem to help us sort of peel back the layers here of this degree 5 polynomial. We're going to try to find all 5 roots. So our list of P is from the constant. It's our factors of the constant. Now the constant being -6, I'm going to have a plus or minus 1, a plus or minus 2, a plus or minus 3, and a plus or minus 6. All right, lots of little factors there of 6. What's the Q going to come from, Freddie? Do you remember that one? Not multiplying them. Eli, where's our Q factors come from? Good, our leading coefficient. Very nice. And that would be 1 in this case, the implied 1 there. So that's real simple. I just got plus or minus 1. So unlike the previous list that had, like, I think our last example had 24 possibilities to check from, Mitchell, how many possibilities are there to check from on this one? Double it. There's 8. And also, what are you chewing? All right, spit it out. Well, you weren't even being sly. You were chowing down on that thing. Like,
I have a question.
what's your question?
How'd you get all the numbers in?
So okay, good question. So Mitchell says, where did our p-values come from? If it's a integer factor of the constant term, then it's on the list of p-values. So being 6, 1 is a factor of 6, 2 is a factor of 6, 3 is a factor of 6, -6, or excuse me, 6 is a factor of 6, and also all the negative ones. And now we're going to put P over Q, which really is just kind of at this point is trivial because Q was only 1. So there's no combo that we're doing here, plus or minus all 4 of those. Those are going to be, so there's 8 possible rational roots.
Wait, how do you divide all your places? How do you
Finish doing gum.
P is the factor of the constant. The factors of the constant factors 1 times 6 is 6. 2
times over. Divide by.
No, I'm talking about. He asked me where you get P from.
Gotcha.
So P is the factors of the constant. 1 times 6 is 6. -1 times -6 is 6. 2 times 3 is 6 and -2 times.
Since that question's come up a couple times, let me just make sure everybody's cool with this. So like the number -6 right there, like if you were going to make a factor pairs list, you would say 1 times -6, 2 times -3, 3 times -2, and 6 times -1. Those 8 factors comprise our list. That's where they came from. You know what I'm saying? What's up, EJ? Are you asking why we use the letter P, or are you asking where that list come from?
Is it like just the constant of like?
Okay, so I love you. I'm not meaning to say this sounding like a jerk or whatever, but that's what I was just explaining to Franklin.
Yes, I heard you.
Okay, perfect. So what you'll do is, like, let me go back to the previous example then. That first example, like we looked at the constant. Now the constant in that one was -10. And so our P list, in y'all's class, I screwed this up. That's why I listed Q and P. So plus minus 1, plus minus 2, plus minus 5, and plus minus 10. Those were the factors of our constant. So that's what makes up your P list. So like if you come across, like we'll see another example here in a little bit. Oh, that one's 6 as well. That's boring. Oh, look at there. Okay, so just to look at coming attractions, here your constant's 20. So these are all the factors of 20, integer factors of 20. So the p-value just has to do with the constant term and all of his factors. And whether you just like listing them out in a line or you do the factor pairs, it matters not to me. But what we're going to do now is we're going to divide all the possible p-values divided by all the possible q-values.
So how do we determine the Q value?
Same scenario.
Okay, except for
Just the leading coefficient. Same situation. So in the previous example, that leading coefficient was 6. And so we had plus minus 1, 2, 3, and 6. And that made up a humongous list of possibilities. And we said, let's kind of test them out. Here, our list is not so big. And what did we say, Mr. Richmond, that is helpful for us to sort of test out some of these values? These are our possible rational roots. How could I find maybe a good one to get the ball rolling? Okay, like you could plug one in, and that would be totally doable, especially considering that y'all Y'all have calculators? Are they out, by the way? Y'all have calculators? Steven's got his out. That boy. Let me go ahead and get mine out. I would recommend maybe looking at the graph as well. Okay, so the graph of this function would be something helpful to consider. All right, let's go y equals, this was our last. Oh, gosh. Get out of here. All right. This is my last one. So let me clear that out. And real quick, y'all type this in with me here. So we'll go to the 5th. And then minus 4x to the 4th. Minus 18x to the 3rd. Plus 38 x squared. Minus 11x. Minus 6. All right, and then I'm going to zoom 6. What does zoom 6 do? It jettisons the previous window that I had put up for the previous problem, which might not be appropriate for this particular example. And I'm gonna look and say, oh, okay, well, here's the graph of this function. Now, as we've practiced before, let's fiddle with our window a wee bit. All right, for instance, I don't need to go all the way out to the left. I can sort of trim that down a little. Maybe trim it down to negative 6. So let's do negative 6. Maybe 7 to the right. Now, here's the trick. How far down should I go? Maybe negative 100. I'll try that first. Maybe we'll go up to positive 100. And I don't want 200 tick marks, so I'll do one every 10 units, and I'll just have 20 tick marks there. Was that high enough and low enough? No, probably not. So let's go back to the window, and we'll adjust it again. Maybe negative 300 and positive 200. And I'll do a tick mark every 25 units. Dang, I gotta keep going. A little more. What do y'all think? Anybody found it yet? Negative 500 maybe?
Negative 500.
Oh, snap. Let's go negative 750. How low can you go? Limbo.
Close. So negative 750 will be close.
800.
All right, that's good enough. That's good enough. And I don't like all those tick marks. So let's go, instead of every 25, we'll go tick mark every 50. Let's go negative 800 just to be consistent. So in essence, what we've done is we've zoomed out enough to where we got a nice, neat picture. Do you have to do that for this problem? No. Nah, you don't have to. But I like a good looking picture. Okay. And this is a good looking picture. Now, Finley, I got a tough question for you, son. How many times does that curve hit the x-axis?
5, 4,
Blake,
5.
how many times do you think it hits the x-axis? The blue curve hits the x-axis more than 0 times.
5.
Freddie?
5.
Christian?
3.
Is your name Christian? 5. BJ?
3.
3 times. Good, googly moogly. It hit 3 times, people. All right, it hits once right here. It hits once right there, and it hits. Ooh. I'm eating some humble pie, baby.
It's twice.
1, 2, 3, 4. It hits 4 times. Shucks. You know what happens when you zoom out too much? Yeah, Nash, that's right. So shame on me. I'm glad I left this original picture up here from my old calculator. Let's consider counting. And here I was busting people's chops, and I should have been busting my own chops. There's 1 right there. It's hard to see, but there's 1 right there. There's 1 right there. And there's 1 right there. Okay, so that's a little weird because this was a degree. Mitchell, why is your laptop open? Gotcha. What was the degree of this polynomial? Degree 5. So we know it has 5 roots. So what's going on here? All right, good thought. But let's go ahead and dispel maybe a little bit of a misunderstanding here. And actually, I want you guys to write something down because I did not do a good enough job of teaching you this when we were learning complex numbers. And I want to make sure you understand this is an exam question that I'm fixing to hit you up with. Okay. And I'm going to quote something, and you just need to soak in this quote. Mitch, you listen?
Yeah.
Good. All right, so here's the quote I'm gonna give you guys. Complex roots occur in conjugate pairs. Complex roots. Guys, they will always occur in pairs. They occur in conjugate pairs. So if A plus BI is a root, A minus BI will also be a root. Guaranteed complex roots occur in conjugate pairs. That will be a true false question on the exam.
You have two roots.
Bingo. So I can't say that, ooh, this degree 5 has 4 real and 1 complex. They don't work that way. Complex roots occur in pairs. So if this one was going to have any complex roots, it would have to have either 0, 2, or 4. I submit to you that it has no complex roots, but it has a double root right here. Did you notice the root around the area of x equals 1? It looks a little funny, right? I could zoom in on that, and my old pictures are more helpful, I think, than the new one, where I was fiddling with the window. Do you see what happens here? It's doing like a little touch and go. Is it actually passing through the x-axis? It's just kind of coming up, giving a little kiss and go back down. Okay, it's what we call a touch and go. So that's the notion of it's an M word. Do you remember what that M word is? Multiplication. Close. It's called multiplicity. We'll learn about it in the next slide a little bit more. So multiplicity. What that means is that it's a double root when something is behaving that way. If the curvature doesn't pass through the x-axis, but it just kind of touches it and goes back down, then that's a double root. Now, from our list, it looks like 6 is one of the roots. So I can synthetically divide that out. And if I get a remainder of what, Stephen, I'll know it's a root. If I get a remainder of 0, then that means it's a root. Franklin, remind me, where did these green, I'm fixing to do some synthetic division. Where did these green numbers come from? Good. The original function's coefficients when listed in decreasing exponential order. All right. Nicholas, please help me with some arithmetic, my friend. Here we go. We're going to do a little synthetic. Are y'all synthetically dividing with me here? Y'all going to follow along? I'm going to see if we can call out 6, see if 6 is a root. Because, by the way, 6 was on my list of possible rational roots. And it looks like on the picture, it looks like x equals 6. So we're going to test that out with Efkeman's excellent arithmetic. Oh, baby. Oh, baby. Okay, is 6 a root? Yes, it is. All right, now, with regards to 1, were y'all cool on how we said from the graph, it looks like x equals 1 is a root. I'll put a question mark next to it. We know x equals 6 is a root, so no more question mark. We'll put a check there. Let's see if Mitch can help me do my arithmetic for taking 1 out.
So bring 1 down. 1. So you subtract, correct? For synthetic division, add.
Tally it up,
So
whatever the
3,
signs are.
3, 3, but -3. Then the -3. That 1, the -1. And it's -1. 0.
All right, Mario.
Why didn't you plug in the first?
Why didn't I start over again with the original function? Okay, so BJ, you missed that class that where we started throwing this to. Who else missed that class? Because what I don't want to call on somebody that that it wouldn't be fair for me to call on. Eli, you were here. Okay, so Eli, would you please take a stab at answering Mario's question? It's a tough question. He says, "Hey, why did you just continue on? Why didn't you go back and start over again?" All right. So it's like when we're culling out, look over there in brown. This is a previous example, Mario. When we cull out our first root, okay, you know what the word cull means? You know what we're doing? Like yeah, if you had like a herd of livestock and one of them was like diseased and needed to be removed from the herd, you would cull it out. You'd take it out and get rid of it. And so like that's what we've done with each time we find a new root. In this previous example, we found that 2 was a root. So we culled it out from the original, and then what was left over was where the other roots were going to still be from. Once you take a root out, it's not going to produce any more roots. And so you would just be like, okay, well, he's out, he's done with. Let me get down to business with the resulting quotient. And so we continue to do this synthetic division. As long as we're getting 0 as a remainder, you take out a root, and then what's left over, you take out another root, and then what's left over, you take out another root, and so on and so forth. It's much like roasting marshmallows. Okay, we did a little roasting marshmallows over the break, and these marshmallows were ginormous marshmallows. Y'all ever roast marshmallows, by the way? Do them? Okay. Are you burnt or golden brown?
Either.
Raw?
Not necessarily. I just don't like it any color on the outside.
I'm a golden brown guy. I'm a golden brown guy. And I'm not a hater. You roast your marshmallows the way you want to, but I'm a golden brown guy. But here's what you sometimes might encounter, right? If you don't cook the fat ones long enough, the inside is still uncooked, and then you'll go and it'll like just peel the sleeve, it'll peel the skin off the marshmallow. And you're like, well, gosh, dog, I'll just roast it again. You ever do that? You roast it again? Okay. And then if it's a huge fat marshmallow, you pull the skin off and then you just keep on roasting until you get it down to where finally the inside's cooked, which is sort of like what we're doing here. You're taking out one root, and here's the core, here's what's left. You take out another root, here's what's left. Take out another root, here's what's left. And so, Mario, we continue to do this synthetic division process until what's left is a quadratic quotient. Because now with the quadratic, I don't have to use synthetic division. I can use quadratic formula or factoring of the CPP. Ken? Yes. Great question, man. Great question. Okay, so multiplication is commutative. If you didn't hear that, multiplication is commutative. So the order in which I call out these roots does not matter. I recommend starting with like a nice easy number. I wouldn't like take out a fraction first, right? But look at this root right here. This root was a 1/2. Okay, could I have taken out a 1/2 using synthetic division at the very beginning? Abso-freaking-lutely, I could have, right? And in fact, let's mess this example up and do that just for kicks and giggles. We'll take out a 1/2. And bring the 6 down. 1/2 times 6 is 3. Negative 40 times a half is negative 20. 46 times a half will be 23. Take away 23 is 20 times a half is 10. And you get out 0. And so you call out whatever root you want to in whatever order you want to. But I recommend don't start with a fraction. That's typically not advisable unless you can't avoid it. All right, Mario, good question. Kenneth, good question. Nicholas. Yes. Okay. So good question. While I'm in the world, are we taking 6 out? 6 was on our list, and it looked like from our graph, it looks like 6 would work. And so we tested it out, and we found that it was a root. And then once you take it out, take out 1. The reason we're fixing to take out 1 again is because of that weird little behavior where it didn't just go straight through. Mitchell, I fear that you are missing a lot in your search for a calculator. So at this point, it might be. I'm not saying you're wasting time. I'm just saying you might consider jotting some things down. All right. So because the 1 is behaving sort of strangely at that x-intercept, we're going to test it again to see if there is multiplicity. And I've already let that cat out of the bag that there is some multiplicity. So why don't we go ahead and do this division? Sir? Yeah. So like imagine, all right, go back. Good point, Nash. Go back over here. Imagine if we had like stopped right there. Well, what the dump am I going to do with this cubic expression? Number one, I don't have the cubic formula memorized. I shouldn't because it's ginormous. I've got to keep bringing things down until I get a quadratic, and then I can apply quadratic formula as needs be, or preferably factoring it. Why? Okay, so maybe we can ask that question two different ways. Why is the number one over here being tested?
I mean, I understand the first one.
Why are we doing it again? Because of the behavior here, because it's going up and it's little kiss and go, little touch and go. Yeah. That's so let me go back to my fancy calculator and I'll show you what's up. Oops. We're gonna completely screw this window up, but that's okay. All right, so you kind of see what's going on here. It's passing through some root over here, IDK. That's probably an irrational root, given that there are no rational numbers in that region, by the way. And then it's coming back up here to 1, so I'll hit trace 1, enter. So I know that that's a root, but because it's not passing through, I think there's a multiplicity there. There's it's doubling up. So x minus 1 and x minus 1 are probably 2 factors, as well as x minus 6, and then whatever the other 2 irrational factors are that would come from my quadratic quotient. All right, let's go ahead and finish this synthetic division out, though.
One for
Would
one.
you recommend doing the division and get like?
Absolutely.
quadratic?
Yep. That's the process. That's heck, and fellas, to be honest with you, I would probably go ahead and on my graphing calculator. I'm good enough at my graphing calculator, and I think you guys are as well. Let's just go back to Zoom 6. Okay. I'm good enough at this point to go ahead and hit trace 6, enter, and say, yep, that's a root. And then trace 1, enter, and say, yep, that's a root. And then I would say, now to find the resulting quadratic coefficient, because the other 2 are going to be irrational, right? I've got to cull out 6, 1, and 1 and be left with my quadratic formula for the other 2.
It's 1 4 1, and then it's also 1 4 1 0 on the bottom.
All right. So like, how would you fill in down here in blue? We got x minus 6, we got x minus 1, x minus 1. Finley, help me fill in the blank here. What would this quadratic one be? You look like you were out in space somewhere.
How about the 1 4 1?
I don't know. You tell me. See, he was fishing. I didn't bite, did I?
Squared plus 4a.
Attaboy. Make sure you're paying attention. X squared plus 4x plus 1. All right. So, how many roots did we say this one was going to have originally? 5 roots. How many have we found?
2.
Try again.
3.
3. Well, yeah, I guess you could be like technically it's 2 unique numbers. One of them was a doubled up with multiplicity. All right. So we found 3 roots: x equals 6, x equals 1, or x equals 1. And then the other 2 are going to come from the what?
Quadratic formula.
From the quadratic formula, which Henry Heil is going to happily quote for us. My seniors were bemoaning the fact this morning in advisory that their pre-calculus teacher is giving them a quiz or a test today over using the quadratic formula. And so you guys, being Algebra 2 trig students, next year, some of y'all may go into a pre-cal or an honors pre-cal class, and it will be assumed that you know what Henry just quoted. So good job, Henry. Andrew.
I get that x squared plus 4 plus 1.
Finley told us that, so I'll let Finley answer that question. How did you get this? All right. So the notion is we take our original function, we call out 6, getting it down to a linear times a quartic. We call out 1, getting it linear times cubic. We call out another 1, getting linear times linear times linear. That's 1, 2, 3 times quadratic. And then that
Stop
quadratic,
dividing those quadratic.
louder.
Like that's why I stopped dividing those quadratic.
Bingo. And at that point, we can either factor or use quadratic formula as Henry quoted. Mitchell?
I could do the 1.
In your quest for a calculator, you missed my explanation for that. We did the 1 twice because of the behavior of the curve at 1 was such that it did not pass through, but it gave a little kiss and go, a little touch and go. I'll go ahead and let that cat out of the bag. It's called multiplicity. There's a lot of information on this screen, but just look at the pictures. Even multiplicities do that touch and go. if a root, Mitchell, is repeated twice or 4 times or 6 times, it will touch and come back. Maybe it'll go down to like a little, what do you call it with airplanes? Do they call it a touch and go?
Yeah.
Yeah, so like where you maybe hit the runway and you keep on going back on up. So that's even multiplicities. Odd multiplicities behave similarly. Instead of just going straight on through, they kind of get a little close and flirt with it for a little while. Then they pass through. Then they stay a little close, a little bit longer, and then they're gone. Like my high school girlfriend. Just kidding. Didn't have one. Kenneth.
Why do you X minus 6 or X plus 6? Because the 6 from the synthetic environment is probably not.
Yeah. So the format is always, it has to do with zero product proper, but the format is always X minus K, K being the number that we've got right there. So it's the opposite of what the number is saying. Correct. And also, what are you chewing? Oh, good grief.
Oh, God.
Franklin.
So X minus 10.
How could I say this? Every time we pull out a root, X minus that root will be a factor. You said that one.
I think we've done this mixed up.
I doubt that. Where do you think?
The other two roots are -4 and -0.
What is it?
So the
Your
calculator
picture?
app,
Gotcha. I would argue that they cannot be, because neither of those
that's what I'm
numbers are
saying.
on our P over Q. So like if I hit trace, what were you saying they are?
So -4, -0.
All right. So when I hit trace equals 0, I get -6. So that's a y-intercept, not an x-intercept.
Yeah.
And then if I hit second trace 2, and then I do my little left bound, right bound trick. So left bound, enter, right bound, enter. It's saying it's about -0.267 and some change. That's an irrational number. So can I peek over your shoulder? Oh, you're using an app to find the roots? Isn't that interesting? I bet they round. I'm not, was that the polynomial simultaneous equation solver too?
Yes.
I'm not uber familiar with that, but look, fellas, Mitch has just brought up a good point. If we wanted to use our polynomial simultaneous equation solver 2, in other words, app 9, and you looked at polynomial root finder, let me look at polynomial root finder help, perhaps. Set up for the polynomial, input coefficients, input solve. No, those are just instructions. Yeah, IDK. I'm not super familiar with it. Second quit. And 6. We're going to quit the app. So maybe it's rounding. That's my best guess. But Henry's quadratic formula, has anybody already run those numbers and got me a nice simplified? Ooh, Blake Green, you got it for me? Michael, you got it for me? Nobody's done the numbers yet. What's A? 1. What's B? 4. What's C? Okay, well, let's plug and chug. All right. The opposite of 4 plus or minus square root of 16 minus 4ac. Hey, remember, have we talked about this before? Where I don't feel comfortable doing the whole discriminant. And so I do b squared in my head, and then I write out minus 4ac. So I don't screw up the arithmetic. Louder.
A and C are both 1.
A and C are both 1. Yes, sir. So we would say, okay, well, what's 4 times 1 times 1?
Oh,
And then 16 minus 4?
Well,
All right, so we got square root of 12. Ooh, now square root of 12 has a factor of 4 hiding in it. So it's 2 radical 3. And then you could cancel out the 2. And so look at what we're going to be left with. We're going to have -2 plus or minus square root of 3. Those would be our other 2 roots. And so for those of you like Nash, I think you said you had gotten an answer, but you weren't 100% sure on it. Beautiful. How could I check to see that that's a good answer? All right, go back to the calculator. And do you remember those roots that Mitch and I were talking about? Look, I'll hit trace. Here's how you can verify. I'll hit trace, and I'll do -2 plus root 3. And guess what I'm going to get out as an output? I'm going to get out 0 because that is a root. And notice that root, positionally speaking, was to the right. Phil, you wait. No, you're not sleepy after.
Come
work,
on,
right?
Philly Phil, bro.
so we're looking
Birthday
at
back.
Yes, great question. Make sure everybody heard that. Mario was asking, man, he's throwing some zingers today. I love it. If the root has multiplicity, you do not have to list it out multiple times. Just list it once. So you'll notice that I've got 6, 1, -2, plus radical 3, and -2 minus radical 3. Those are the 4 roots. It would probably, like if this was an AP class and you knew you had some sticklers that were like grading this as a problem, you would definitely want to talk about how 1 has a multiplicity of 2. That your 5 roots, this one was a repeated double root.
Which one? When you put in -2 minus the square root of 3, it doesn't give you y equals 0. It gives you y equals -2 plus 0.2 e.
-2. Oh, what's that called? Scientific notation. That's like a number that's really close to 0. It's the calculator's having trouble with the rounding. So to Mitch's point, -2 minus radical 3. Let's see what my calculator does. I'll hit enter. Yeah. So -2.2 times 10 to the -11 is, I mean, like minuscule. It might as well be 0. So the calculator is having trouble because when I entered that irrational number in, it, for all intents and purposes, it cut it off after it looks like 7 digits. It cut it off. It rounded it. Hence the rounding error there. I didn't get purely 0. But we could take it to the bank. We could say, yeah, that is a root. Correct. If those numbers continue to, because an irrational number like -2 minus radical 3 is non-terminating, non-repeating. Kenneth, what's up with your calculator? Oh, gotcha. All right, so 6 and 1 originally were on our list here and here. We were curious that we said, ooh, it looks like those are 2 roots. So we synthetically divided them out. This one, because of the behavior right there, we divided it out again. And once we got it down to a quadratic coefficient, we said, all right, those are my 3 linear factors. And then this quadratic factor we split up using quadratic formula. Boys, this is heavy duty, like honors pre-calculus level stuff that y'all are working on right here. Not something to be taken lightly. The basic portion of this exercise is, can you come up with P? Can you come up with Q? And can you come up with P over Q? That's like low hanging fruit, regular old stuff. They do that all the way up and down the hall. You guys, y'all are the big boys. Y'all are taking it now, and you're doing things like culling it out using synthetic division, graphing it to see if there's any multiplicity, etc. Listing it out as a product of linear factors. From this page right here, did you guys catch the 4 graphs? These probably are the important pictures from this. That an odd multiplicity, it doesn't just pass straight through, but it does a little shimmy around the x-axis. And the double root does a touch and go, a little kiss and go. The even multiplicities. Okay.
If you have a quadruple root,
What does quadruple mean?
there's 4 of them. So
Yeah,
it
yeah,
would
yeah.
be 4 times.
Say it again.
So if it was a quadruple root, well,
Yeah. You'd have like x minus 1 and x minus 1 and x minus 1 and x minus 1.
So that would just stuff, you just synthetically divide by 4 times.
For real. Now I'm curious. Can anybody? Use our binomial expansion theorem that we talked about 2 or 3 weeks ago, and real quickly tell me what this one would yield.
Kenneth can. Oh, I forgot it.
You remember we used Pascal's triangle?
Yeah. Oh, yeah.
Uh-huh. I'll spot you up. It's gonna start with x to the 4th, and then x to the 3rd, and then x to the 2nd, and then x to the 1st. And then it's gonna have 1 to the 0, 1 to the 1st, 1 to the 2nd, 1 to the 3rd, and 1 to the 4th. Because this is a minus sign, it's gonna alternate, so it's gonna be plus, minus, plus, minus, plus. And then I think that's it. Now I need Pascal's triangle for the 4th row. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 0, 1, 2, 3, 1 more row. 1, 4, 6, 4, 1. All right. Is that ringing the bell? You do not have to know how to do that.
A little bit.
But we have discussed some of that up to this point. All right. So the reason I'm saying that, come back over to the pull down screen, is suppose, let's see if this dog will hunt here. What we've got is we've got a polynomial function. We'll call it f of x. And it's 1x to the 4 minus 4x to the third plus 6x squared minus 4x plus 1. And guess what this function looks like? It's got a multiplicity please say no. Is that a parabola? Correct. It is not a parabola. Does that resemble sort of kind of like a parabola? Okay. But guess how many roots there are for this particular function? There are 4 right there. And guess what all 4 of those roots are?
Or 1.
1. And how would we go about verifying that as an exercise? Man, oh man, we would say, all right, 1, -4, 6, -4, 1. And then we would start peeling off those layers, peeling off those dollar bills and slapping them down. 100, 200. Nobody. That's okay. It's a Bono song. It's Bono and BB King. -1. Y'all know who Bono is, right?
Yeah.
Right, from U2. And we know who BB King is because we live in Memphis. Oh my goodness.
You don't know who BB King is?
I want to slap you right now. Is that bad?
Does he have his name spelled weird?
Bono, just Bono? Yeah. Looky there. All right. So you see what I'm saying to Mario's point? Like this one, we would literally pull out x minus 1, x minus 1, x minus 1, and then the remaining linear quotient will be x minus 1.
Why did we only pull it out 3 times?
Louder?
Why did we only do it 3 times?
The result would be our 4th one. The quotient will be our 4th one. So like each time you pulled out x minus 1, that was the first one. And then another x minus 1, that was the second one. And then another x minus 1, that was the third one. And then this one right here is x minus 1. And that's our 4th one.
Oh, so that if you did that by 1, it would turn out the same way.
What do you mean
If
by
you
1?
synthetically divided that by 1, it would turn out the same way as it is. When
Synthetically divided what by 1?
Linear function.
Synthetically.
If you divided the linear function, you
Oh,
divided.
this down here?
Yeah, sorry.
Oh, heck yeah. Yeah. Well, look at what you get.
You'd get 1 and -1, same thing.
1 times 1, 1, 0, and you get 1. And so maybe we could say
Yeah.
that was our 4th one, and then we're going to times that by 1, which is trivial at this point. Mitch, that's interesting. I'm glad you dived a little further on that. So we got 1, 2, 3, 4, all 4 of our roots, and then this would be just boring because at that point it's times it. And it doesn't provide any extra roots or anything like that. Okay. Ooh, I love this kind of stuff, y'all. Y'all are stretching your mental muscles right now, except for Finley, who's over there laying his little head down because he's sleepy. All right, let's see if we can go through this one a little bit more. Like I took my time and explained that one like in great detail. Why don't we take a stab at this one and just kind of start rocking and rolling? Okay. So, Aiden, you up for some? That's weird. I shouldn't ask that. Aiden, give me the list. I was gonna say, are you up for some P? That's weird. So give me the list of P.
Would we have to list
Oh.
out? That's my money.
Just as an exercise.
Is it okay to give engines? Like
Those terms that the quadratic term you skip is not affecting P or Q, but it is affecting our synthetic equation. Aiden, sorry, go ahead. Beautiful. All right, Freddie, do the Q. What's always a factor? What's always a factor? 1. And then? Good. All right. So now, excellent. All right, now let's, gosh dang it. That's a little better. Let's get Steve Areno to do P over Q. All right, what do you think? 1 over 1? 1 over 2. We're going this list over that list. We're going 1 over 1, 1 over 2, 2 over 1, 2 over 2, blah, 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 blah. Keep on going.
You 3 over 1 is 3. And
Here's how far I've gotten on my list. I did 1 over 1 and 1 over 2. Now you carry on, my wayward son. There will be peace when you are done. Don't lay your weary head to rest like Finley was. And don't cry anymore. Very good. That's bonus point. Good job, Steve. Yeah.
Yeah,
What's wrong with me assigning Steven a bonus point? I'm at my liberty to do that. All right, so 2 over 1 is 2. 2 over 2 is 1, which is already on our list. 3 over 1. Uh-huh. Uh-huh. It's already on my list, so that list is done. Very nice. All right, so 2, 4, 6, 8, 10, 12. 12 possible numbers to test out. Blake, where do I go to? We're trying to do this on that speed, right? Where do I go to like get my foot in the door? Okay, let's make sure that we let the people answer when I call on them. This very, 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 very rough sketch. It looks like -2. If you wanted to plug that on your calculator, you could. Is -2 legitimately on the list that Steven just gave us?
yeah.
It is. So, Fredo, what do I do with -2? To test whether or not it's a root. I don't want to do any multiplying. Mike, we do want to synthetically divide. Cuidado, mi amigos. We have to be careful because we skipped a term in this particular function. So when you synthetically divide, put in that 0. That's where this 0 came from. Please make a note to that effect in your notes. Eli. Yes, I don't think I'm going to have time to get to it today, but there is a way to take these big fat daddy lists. I don't remember if I mentioned this last or a couple weeks ago or not, but like look at this ginormous list of like 24 daggum factors. What do you mean? No, we're not going to combine any, but we're going to take this big old fat list, and what we'll do is I'll teach you a technique of figuring out which ones from the bottom of that list are to be chopped off, and which ones from the top of that list are to be chopped off, and to kind of narrow it down.
Is it usually what they're factor?
So if you didn't have a calculator, there is a way of sort of saying you guys are too low and you guys are too high, and so this is my meat and potatoes. And then you would just individually, like if this was in the 1800s, you would be individually just doing every single one until you got to a point at which you could get your foot in the door. Mitch, I didn't hear you.
Are they usually fractions?
This is called the rational root theorem. And so, yes, you will have fractions that usually show up on these lists. I don't think our last example did, but that was just because the leading coefficient was 1. Anytime the leading coefficient.
Will these fractions ever be the answer?
Yeah, we saw that in our first example. Mm-hmm. Yeah. So this one had -1/3 and +1/2 as. But I don't want to start at those fractions if I can avoid it. I want to start at the integers. So like we did 2 and 5, and that was an easier way of doing that there. Great question, man.
I did this because
Does it work out?
it does. It goes so on the second row, -4, 8, and -6. That's 2, -4, 3, 0.
All right, so that's our A, B, and C. Henry quoted the quadratic formula for us earlier. I'm not going to re-quote it here, but I am going to say, because this one only touches the x-axis once, this is a cubic function, and it went straight through the x-axis, so there's no multiplicity, no funny business, no touch and go, no, any of that. What are my other 2 roots going to be? They're going to be complex numbers that occur in a conjugate pair. When there's only one x-intercept and there's no funny business, no multiplicity, and it's a cubic function, now though the other two are going to have to be complex. And so this does not factor out. I shouldn't even try to mess around with factoring it out. I'm going to go straight to quadratic formula. Okay. And so here are my roots. We've got -2. And then that was my one rational root. That was a good one. And then let's do some scratch work over here. 4 plus or minus 16 minus 4 times 2 times 3. That's a negative discriminant, mind you. So we're going to have to pluck out the I. 4 times 2 times 3 is 24. And so is that an 8? And 2 radical 2. And so 2 plus or minus I radical 2. No. Hold on. I'm trying to do too much. There's going to be a fraction in there. What'd you guys get when y'all did that? So maybe a 2 plus or minus. Let's put it in A plus BI form. Let's do that. So 2 over 2 would be 1 plus or minus square root of 2 over 2 I. I think I like that. Make a note in your guys' spiral. Make a note. QF. That's where those two roots came from. 1 plus or minus radical 2 over 2 I would be probably the best way of expressing that. And I tried my best to go through that one at speed, sort of show you what it was. Show you what it was like. How many roots did we find? We found all 3 of them. It's a cubic function, and congratulations, you found all 3 roots. Before a month ago, you as algebra students would have been stuck, and you would not have been able to handle any such equation. You would have been like, Coach Moore, I don't know how to solve that equation. Now you did. You use your rational root theorem, come up with a list of possible rational roots, find an acceptable one on the calculator or by guess and check, as Eli mentioned, and then get your foot in the door, call out the root, bring it down to the quadratic form. P and Q, and is this a root? How do you know? Show me synthetic division. Yes, and let's look at the delta. Sir? What was the question? It is due today at 3. Let's pretend like that says Wednesday at 8 or Wednesday at 9. Problem set. Our normal weekly problem sets that you're gonna do every single one of them. You're gonna get a 10 out of 10 on all of them this quarter.
It's hard to get competitive, so.
Yeah.
Maybe I don't want to. Who's asking me that? Steven's asked me that? Oh, let me take out my pen here. No, I'm kidding. I wouldn't take a bonus point. It is hard. I know. It's very hard. But if you come and ask me about them, it makes it much easier. That's fair, isn't it?
Yeah.
Okay, so
Because it's due 2 days from now, so I can.
yeah. You can ask me tomorrow being Tuesday. You can ask me Tuesday, Wednesday, or Thursday, and it'll be due on Friday. All right. So, what are all the possible integer roots? Okay. So, these roots are hiding. Revisit the integer roots theorem. I didn't teach you guys the integer roots theorem, but what's nice about it is that it's a little bit easier than the rational root theorem. I'll show you what I'm talking about here. So all you gotta do is list out the possible factors of your constant term. Okay. And once you've done that, it says the rational root theorem expands the integer root theorem by taking P over Q. And so like this is an example with some rational roots. But for us, we're just looking at the constant term divided by the coefficient term. So your list of P right there takes that into consideration. I like their explanation for most of these problems, right? And so like I've been asking you guys, it says separate them by commas. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. List out all the factors of negative 6. Oh, snap, crackle, pop. Thank you. All right. And then it says, okay, now do P over Q. Now, Q being 1 here, I'm just going to rinse and repeat. It says identify 2 roots. So what would it be? Negative 2/5. And what's that going to be? Add 9 divided by negative 10, so negative 9/10. Oh, that's an example, isn't it? For example. Identify 2 roots as fractions. I would probably just pull out my calculator and decide which of these 8 numbers looks good. And then I would test it out using synthetic division. I wonder if they do their synthetic division on these. They do synthetic division.
Nothing like what you just.
Roots. They're structuring their P and their Q list a little bit differently. Question. Rational root expands on the integer root theorem. We know that. Here, for example, it's quadratic with 2 rational roots. Identify 2 roots as fractions. They do want me to do this one. So negative 2/5 and negative 9/10 roots each. The numerator is a factor of which one? What's our P? Where our P comes from? Constant. And then the denominator is, there we go, expand the quadratic form. We want to multiply 5x times negative 50x squared. Quadratic to the form. My caps lock on? Yeah, my caps lock was on. Squared. What's 9 times 5? 45 and 20, so negative 65x minus 18. Numbers 2 and 9 are factors of the constant. 5 and 10 are factors of the leading coefficient. Rational roots would have to be numerators of the rational roots. And form the constant term. They're multiplied. The denominators multiplied to equal the constant term. Incorrect choice. What did I type wrong there, Mitch? The denominators would have to be added. Form the constant term. Bump. I don't know. Multiplied in part to. I liked this better when I was assigning it because it made sense then. The numerators of rational roots would have to be multiplied to form constant term. And the denominators would have to be multiplied to form the. Did I not write that already? I did both multiplied. Multiplied. Denominators have to be multiplied to form the constant term. Multiplied to get formed. Oh, because I'm an idiot. Good gravy. I already did constant term. I did constant term twice. And then possible numerators. All right, so you tell me what would all the numerators be? Plus or minus 3, plus or minus 1, plus or minus 3. What would all the denominators be? Plus or minus 1, plus or minus 7. Now, this is where we would be P over Q. So 1, 1/7, 3, 3/7. Plus or minus 1, plus or minus 1/7. Plus or minus 3. Don't forget my comma, Mitch. Plus or minus 3/7. And it says, yay, good job, Coach Morgan, you finally got there.
It seems way too complicated.
They're guided questions, so they're supposed to just take you through it. You only have to do 2 of them. No, I just randomized it. And then you asked to be up front, so I'll put you up.
Maybe computer moved everybody over and then scraped.
No, I literally just took y'all's,